I will talk about several things. So the topic is news from research. So my name is Sven Oehme. I'm part of the IBM Research team. I'm working on spectrum scale, also known as GBFS, for over 10 years. I don't even remember exactly how long, but for a long time. And I primarily focus on performance engineering. And so I wanted to talk a little bit about why performance engineering actually matters. And some of these things are exactly because of some of the work we're doing for Coral. But there's far, far more to that we're doing, which typically people don't actually even see about. Because there's a lot of things going on in the background which are not necessarily visible directly in the product. But I thought it's an interesting, different topic to talk about so people understand some of the things we're doing in the labs. I'm talking a little bit about spectrum scale with NVMe. It's a pretty hot topic. Everybody talks about it. What can you actually expect from NVMe? So I'm trying to focus on a couple of performance experiments with NVMe. I also have done some measurements with NVMe over fabric devices. You might see a lot of vendors talking about those lately too. Most of them are still ChartWorks, but there are actually some out that actually even work. And I've actually done some performance testing with some of them too. I'm talking about a little bit more details on ESS GF2 performance results. And I'm talking a little bit about IOPs, because somebody asked about IOPs. I could probably talk for at least 2 hours about IOPs. So I put it at the end because otherwise I'm not getting to the other points that I wanted to make. And so somebody basically needs to cut me off. And at the very end, Dean Hildebrand will talk a couple of minutes about Docker and some of the work we're doing around Docker. Okay, so performance engineering matters. So we just heard some of the requirements. I'm not repeating that. I just learned that one of the problems potentially even got bigger for me. I thought it's only 1 terabyte we need to deliver, but seems like it's actually 2.2 terabytes for random I/O. So there's a typo on the chart. But besides that, you've heard about these requirements. So you've seen that some of these requirements actually coming directly from ORNL. Some of these requirements are actually part of the Coral RFP that we had to answer to. And so as Oral and Gautam already mentioned, these are the kind of things that we need to deliver. But it might be interesting for some of the people, how can we actually deliver them? So it's great to understand, okay, these are requirements, but what are actually the challenges involved in actually getting to those numbers? And as I said, there is a lot of very detailed things involved. And one of the things that is very important to understand for people, actually what kind of innovations in the overall storage system around scale need to happen to basically make this work. So let's start with disk drives. Disk drives is always a very interesting topic, because you get very different answers depending on who you talk to. So when you go to a disk vendor and ask him how fast is a disk drive, the answer you're going to get is at least 150 megabytes per second. Some going to claim it can do 200 megabytes per second, and if you have 15K SAS drives or so, they might even do 200 or 250 megabytes per second per drive. So if you go to your block storage seller and ask him, so how much performance can you expect from a disk drive, the numbers typically go a little bit further down. So people talking about 100 megabytes per second anymore. And if you ask an application person what he thinks a disk drive actually performs, it's always too slow, because they always have to make special tweaks to get the performance out of the drives that they're expecting. And they don't understand, okay, why can't that thing deliver what the people on top of me basically always tell me how fast these drives are? Because some of the application people know my lab has thousands of these drives. If I do the math, all systems in the world should deliver a terabyte a second. And so if you talk to your HPC admins, these are then typically the people who understand a little bit more about it and say, well, the answer depends. Because it actually really depends on what workload patterns are that you're running against drives to see what you actually get out of them. So who is right and how fast are they really? That is a question that we always ask ourselves as well, and try to figure out how we can push the boundaries higher and higher and higher to get more and more to these numbers that you see on the very first top. So the first thing is to ask the question, okay, what actually influences the total system speed? Because only if you really understand what influences the speed, you can actually fix things. So you need to understand first, where is the overhead and where are the problems coming from? So there's obviously, if you start at the very, very top level, there's file system overhead. So every file system adds overhead. And in fact, just to measure it and to show you how little that actually is with GBFS, I have a couple of interesting charts when we're looking at the NVMe data. Because given that NVMe is the fastest device you can get, or the fastest device you can get these days, you measure against the raw block storage, and you put a file system on top of it and compare the two. That shows you very nicely the difference in overhead. And so I have a special slide for that. So controller overhead. There is always this religious debate about software versus hardware. What is better? And I don't think there is actually a very simple answer for that, because it depends on how good your software is, and it also depends on how good your hardware is. So rate mode, same thing. This is a practical, simple question of math. So if you know how many physical IOs per second a drive can do, based on single, double, or triple parity, one can actually calculate exactly, if you have no limitations in these top 2 or 3 layers, how much can you actually expect out of a drive. So if you have to do a read, modify, write, it's typically 6 IOs. So if your disk could do 600 IOs a second, which it can't, you would be able to get 100 read, modify, writes out of every single individual disk. I just picked 600 because it's easier to calculate. But essentially, these are things that are very simple to do in math. So cache efficiency, here's where it's get really, really complex. So the first 2 things, you can have estimates, guesstimates. You can basically kind of, figure it somehow out, either through math or some simple measurements. When it comes to cache efficiency, things get very, very dicey very quickly, because there is huge difference in how you actually implement RAID protection or the RAID scheme in general. So if you do this in a hardware layer, the hardware layer doesn't see very much. It sees zeros and ones coming in various patterns, and it can only react to basically what it's seeing. If you have a RAID implementation that is part of the file system, like we have with GNR, which is shipped as part of ESS, actually the ESS devices, or actually the GNR software stack, has a knowledge of the I/O context. So that means the GNR layer actually knows, is the data that's coming in metadata? Is the data that's coming in data? A traditional hardware implementation can't deal with that. It doesn't have that context. And so this is where you typically see the majority of the differences with all these different architectures in terms of storage devices. It's actually not how fast is a disk. It's actually not how many IOs per second you get out of a disk. It's how efficient is the cache algorithm in the devices, and how much does it understand which things pollute the cache, which don't pollute the cache, and therefore basically the context of the IO is absolutely critical and important. And we will see some of that when we're talking about these gigantic create rates, for example, that we have to do, because if you understand there is a lot of teeny tiny IOs coming in that are all creates that happen at the same time, you can make optimizations for that. So then application access pattern always matter too, random versus sequential. Actually, this is slightly overrated in some terms, depending on how great your cache capabilities are, but I have a specific, I talk a little bit more about that later. And then the thing that is actually the most important thing is the access patterns that the disks see. So it doesn't really matter what your application does on the top. If you read sequential or read random, doesn't necessarily mean that your application, or actually, that your disk actually sees random or sequential access. If you take a large distributed file system like Lustre, Ceph, GPFS, pick your favorite one. If you have a large enough system and you're doing sequential I/O, the disk storage subsystem underneath see 100% random performance. So why is that? Because you chop up each large file in teeny tiny portions, and you distribute across all the arms in the system, which essentially means every single individual disk will only see 100% random performance. So looking at sequential performance numbers is very, very useless, because if you have a larger system, you will never get that out. In fact, what you're always falling back is essentially 100% random performance of the disk drives. So the last one is probably one of the most critical and most important one when you look at what you can expect from a distributed storage system. So what I did in the lab is I just grabbed a couple of totally different random drives that I found, stuck them all in the same enclosure, and run one single, very simple performance test over it. So it's a performance test that's actually performed through GPFS. So it's not a block level test. The block level test would have revealed essentially the same thing, but this is done actually through the file system layer to see how well a disk drive performs. And so what you see here is different models from different vendors and different sizes, but they all get one and the same workload. It's always 2 megabyte large IOs, 100% random over the entire capacity of the disk, and basically all with different numbers of threads. So I start with a very, very small queue depth, and I ramp it up to 63. The reason I picked 63 is because most disk drives can handle up to 64 concurrent IOs. This is basically the maximum optimization point for this drive, and so therefore I measured the curve. As you can see, basically after about 15, 16, not much happens anymore. So if you push more workload in it, there is actually very, very little difference. But what you probably noticed, but just looking at the graph, and this is not just one single disk I picked out, I actually sampled several disks of the same type, you see there is a massive difference in performance. So if you look from the bottom disk to the top disk, we're talking about over 20% disk performance. And again, this is not a specific drive because nearline SAS drives have typically a variation already by about 10%. So you see that is significantly more than that. So there's massive differences in disk drives, while most storage vendors tell you disk drives, and that included me, by the way, before I made these charts, the disk drive technology hasn't evolved for the last 10 years. And actually, in fact, that was wrong. So the disk drives haven't really evolved, but what has evolved is some of the caching algorithms and some of the destaging capabilities in the drives. So they put more buffers into them, there's more capacitors in them, and so they have better ways to basically reshuffle things under the surface of the controller to basically get some more performance out of it. And so you see, disk drives actually still get faster. You don't see that actually very frequently. Okay, so the next level, I picked one of those drives and run a couple of different experiments. So this is now one single drive that I picked out. It's a 4 terabyte drive. So the 4 terabyte drive, I now took a different workload pattern. So if I use a 1 megabyte random IO work size, a 2 megabyte, a 4 megabyte, and 8. So one funny thing I found is that actually the 4 megabyte didn't really perform any different than the 2 megabyte, except for the very first few QDEPs. So, but where there is a significant difference is the 8 meg. And I bet if I would tell the vendor of exactly which disk drive I said, they would look at the system, they'll probably find either a bug in their firmware, or they find that there is some issue with the destaging mechanism at that particular threshold of the drive. There must be some threshold where they basically changed some strategy to the drive, and that's why I see a significant difference here. And basically, you won't gain while you should gain, and in fact, you see if you take the one bigger block size, there actually is a gain. So, but you can't leverage that 4 meg, and I bet this is basically a firmware problem. But anyway, so I took this single drive and basically ran this experiment. So why did I do all that? I did all that because today, when you look at an ESS system, when you do all the math with the numbers that I've shown on the graph and you basically multiply the numbers that we've seen on these 2 megabyte block sizes of one of those medium drive systems, you will see that the performance numbers we get out of an ESS system is essentially the performance of a single individual disk drive multiplied by 348 if you have a GL6. So you see there's basically an almost linear scale from the single drive to 348 drives. So why does all these numbers now matter? It's very simple. If we can figure out how to tap in, and you see this graph actually is calculated based on the previous disk's performance number, which is why there is no difference between 16 and 32 megabyte tracks, but there is an increase to 64 megabyte tracks. So if we can figure out how to get these larger block sizes in place in ESS and also in the file system, the end user will gain at least a 20 to 30% additional performance improvement on top of what we already deliver with the systems today. And so that's why we did all this work to figure out are there actually any benefits and try to figure out how we can actually leverage that. So, but as some people already pointed out, Bob, for example, you can't actually leverage 16 meg block sizes today with most applications. So therefore, I have one other topic that I have to insert in between before we get to that point. But actually, the two things go together. So if we figure out how to gain more bandwidth with larger block sizes, we also need to fix the other problem, which is basically the size of an individual allocation unit. And as I said, I have a separate chart for that. But before we get there, I need to talk about the second problem, because I want to start with the fundamental infrastructure issues first. So this was stuff about disk drives. So let's talk a little bit about network. So the next problem is, so let's assume you get these drives faster and faster and faster, and you can actually get more and more performance out of these systems. Somehow you need to get the data from the storage system to the client and vice versa. And so why do we need to keep up with that? So one thing is what I just talked about, which is drives getting faster, even very slowly, but they still get faster. If we make some of these software enhancements, we can get even more performance out of it. Another driving factor, obviously, is flash everywhere. So there is more and more customers to say, why even bother with disk drives? You know, if I want to get the performance numbers, deep flash, for example, is just a prime example. There is other systems around, but basically cheap flash is kind of going in all different spaces. And while it might not be at the price point today for everybody, I could very well see in 2 to 3 years from now, these really big data flash devices are at such a low, cheap price point that they might start basically competing with disk drives, because the disk drive capacities are not getting significantly larger anymore, which so far was the prohibiting part why flash can't really catch up. So if disk drives don't get much larger anymore, flash prices will continuously coming down. there may be an inflection point in 2 to 3 years if somebody figures out actually how to build that much flash, which is a totally different problem. But these are driving factors. So also, customers always need to use or want to use latest networking technologies. So 100 gigabit Ethernet is something we already test in various configurations. We have customers using 100 gigabit InfiniBand. You can't really scale up NSD servers unlimited. At some point in time, it gets harder and harder to do that. So therefore, the point was we need to figure out how to make the existing communication code far more efficient. And as Gautam pointed out, there is all kind of lower level things we've already done. But I thought it may be a good idea to show just a couple of results that you actually get by some of this work that we've did. And this is actually, by the way, stuff we already shipped in 4.2.1, so the release that came out a couple of months ago. So one of the things with all this rehaul, and I'm not going into many details again, repeating what Gautam already said, where we basically eliminate a lot of locks or made things significantly more efficient, that lead to a couple of very interesting results. So what you see here on this chart is from a single client writing sequentially data into a single file. So it's only one node, but it's writing into one single file. And at the very end, it does an F-sync, which means it's not coming back until all the data actually is really destaged to the drive. And so the result is that we're getting around 16 gigabytes per second throughput for that single operation. So that's a single client that actually has 2 EDR ports connected and is capable of writing at 16 gigs per second. When you look back at the previous version of the RPC code or the RDMA code combined with the RPC code, the maximum number people have experienced in the lab, only under some very extreme conditions and super heavy tuning, was around 7 to 8 gigabytes per second. But that was kind of the absolute maximum we could achieve. So that was actually an untuned test. So this was just basically the code fresh out of the press, so to speak. We installed it. We set one single parameter, which is basically the worker thread parameter that we newly introduced. And after that, we got a 16 gigabytes per second rate. So if you go about past 2 ports, we might actually be able to deliver more performance. I haven't had time to rerun this test with a larger IB fabric and more ports connected. But 16 gigabytes per second is basically what a GPFS client these days is capable of writing. And that is into a single file. So if you write across multiple files, it's a whole different discussion. It can only go up. But the single file case is always a really tough one.
Was it a dual EDR?
This was with 2 EDR ports connected on one client. One client with 2 EDR ports, yes. So it's not the maximum that EDR can deliver. So the theoretical maximum would be around 22 gigabytes per second. So we are below that, but as I said, there hasn't been any, we haven't even looked at why did we not get 22 gigabytes per second, but that test was with basically 2 ports connected. So another side effect of these changes is that we significantly got the response times down. So if you want to go into flash, and if you want to go into low latency devices, you need to get latency down. And it actually doesn't help to really layer things on top of each other. You need to cut things. And so we basically made significant enhancements in the RDMA code to cut through a lot of layers that we had in the code before that we eliminated to get the pass lengths down, eliminated locks, as I'm repeating myself on, but we basically cut a lot of the stuff in the middle in the RDMA code out, and with that we got very, very low response times. So what you see here is a test that reads sequentially, but with direct IO, so there's no prefetch involved, but it basically reads sequentially data in 1K increments with a single thread from a remote ESS system. And the transfer times you see varying somewhere between 50 and 80 microseconds per request. So this is the total end-to-end round-trip time from the client application submitting an I/O, going over the network, reading it essentially from the media, returning it back over the network to the client. This is the response time you're getting. So you see it's very, very low performance data. And actually when you get into these response time numbers below 100 microseconds, it basically means that the network communication is essentially as fast as flash media is. So this is the thing people always struggle with, is the network the bottleneck? Well, these days, if you have a very good implementation of network code, the network actually can be faster than the physical locally attached media. That doesn't mean it doesn't add any overhead, but the thing is if the media alone already requires 100 microsecond response time and the network requires less than that, so yes, it adds overhead to it, but it's not like it's the big pole in the tent. Okay, so that leads to the topic that kind of Bob introduced earlier, saying, well, nobody can use 16 megabyte block size. And yeah, I agree with him. The big if is, if you have a very, very mixed number of file sizes. So if all your IOs are teeny tiny, you have only 4K whatever files, that's not really a big deal because they all fit into the inode. But if you have between your max block size and your inode size, a large variety of sizes of files, that's where the problem starts. And I show this in a few seconds on a couple of very interesting results. So we support all these different block sizes today, and the reason we support them is basically to exactly fill that problem. So we basically push the problem to the end user. So if you know what your average file size is, that's the block size you should choose, because then you will get the best performance out of it. So while that worked for a lot of years, now we get to a point where that just doesn't work anymore, because customers have this extremely mixed variety of files, very, very small, very, very large, and basically today they have the choice between waste space or waste performance. And neither of them is really a very good answer. So you want to have the combination of both. So how do you solve that? Well, the easiest thing is you just add more subblocks, because the limiting factor here is that from the very beginning of GPFS we limited the number of subblocks per full block to 32. And so when you had a 1 megabyte block size file system, which was the biggest block size we supported for a very long time, 32K didn't really sound that bad. So with a 16 megabyte block size, a 32th of that is 512K. If we go to a 32 megabyte or 64 megabyte block size, we're talking about fragments of 1 or 2 megabytes in size. So that means if you create a file which is exactly 4K in size, it's going to write 2 megabytes into your file system because of zero padding and other things associated to that. So therefore, it has a significant performance penalty for small files. And if you take the small block sizes, you have a significant performance penalty on large sequential access patterns to the file. So how do we fix this, and what will it change? Well, the best way is you measure it. So what we did is we basically introduced code which hasn't shipped yet. And I don't think we have even committed an exact shipping date, but it's going to be sometime next year. So that's the only thing we committed, sometime next year. And basically, you see 3 times the exact same test repeated. The first test is a 16 megabyte block size file system using MD test. And the first test is, this is 421 base code, and this is basically 3 iterations and the number of file creates, stats, read, removal, creates of the whole tree, and the removal of the whole tree you get. And you see this teeny tiny number of only 2,237 creates per second. So why is that? Actually, it's not that the file system couldn't create more, which is, by the way, one of these big misconceptions people always have with MD test. One of the most well-hidden secrets for some reason, and I don't even know why, MD test is primarily client-side limited, not actually storage-side limited, except when you have a very large block size. And why is that? Because of exactly the example that I just mentioned, which is when your file create is bigger than 4K, it doesn't fit into the inode anymore, which means it needs to allocate a subblock. Which means the system basically ran at a rate of over 10 gigabytes per second when we did this create test. Because each of these 2,237 file creates wrote 512 kilobytes worth of data into the file system, therefore into the storage subsystem, and basically burns all your bandwidth of the drives by very little input but gigantic output. So the second test, we used the 422 code before it got released, and we added an enhancement where all we did is basically we padded all the zeros. So basically when we write, and by the way, this test creates 32K files. I forgot to add that actually to the title. But these are all 32 file creates. These are not zero length file create, which most people test with MD test. So the second one, we added a zero padding. And now you see we're almost getting 13,000 creates per second. Because now actually the client only has to transfer the 32K instead of the 512K to the storage. Problem is, because it's zero padding, it means we don't write the IOs to the storage system, but the storage system still have to write it down to the disk, which means you're still wasting a lot of bandwidth, but now it's more on the back end versus from the file system to the storage device. And so the real solution is the last one, where we took the 422 code and basically enabled the more than 32 subblock code. So what you see now is the rate goes up to about 40,000 creates per second. Again, this is all the same hardware. There is no difference in hardware. There is no difference in setup. The test is always exactly the same test. The only difference is the second one has zero padding enabled and the third one has more subblocks. And so with the current implementation of the subblock code, we basically allocate subblocks in increments of 4K. So that means basically for a 16 megabyte file system, you're now going to have 4,000 subblocks. And so that now allows you to basically run at maximum speed for sequential or large block random workloads, but at the same time, you're not wasting any more capacity, and you gain a significant performance improvement I mean, it's almost 18, factor of 18 compared to the current shipping code and the code that we targeted to basically meet these Coral and ORNL requirements that we're going to go forward with. There's a question?
And yes, will you be able to get that just via the upgrade on an existing file system, or will this require the
Very
creation
good
of
question.
new
I
file
knew it's
systems?
coming, and I was afraid of that because the answer, unfortunately, is no. So the answer for that is you basically have to create a new file system. And the reason for that is, I mean, I think Yuri had a very long story on that on the mailing list too. Doing something like that in place is impossible to ever get right. So even if we would be able to come up with a code to do that, which we could, there's going to be so many corner cases we will never ever going to get that right. And therefore we decided to not do that. So this only works if you create a complete new file system. And what we need to work on is we need to figure out how to make it easier to migrate from an old file system into a new one. And that's going to be the answer for that. But you will not be able to do an inline upgrade of an existing file system with that because there's just too much danger involved. It's just not going to happen. So one of the things that is very important, and I really get very frustrated from time to time about that, so I can't state that more than enough, sequential bandwidth of storage subsystems is meaningless. Don't even ask a vendor for that. If you get quoted a sequential performance number, throw it in the garbage. It's not what you're going to get. If you run a system, even you run with cluster mode, which Coombs also showed in the previous testing, these are great numbers for doing a big hero number for performance. It's not going to take more than a couple of weeks, and the system is going to degrade. And it's going to degrade at least to the point of scatter, at least. So don't even go there. So if you want to have a high-performance system, ask, like also the Coral team is very aware of, ask for random performance numbers. Because if you have a large-scale system, that is the only number that's going to matter, because all your I/O is going to be 100% random I/O. So if you see numbers at the 40, 50 megabytes per second range, something is not right, because people can do better, and I demonstrate that on the charts. We can easily demonstrate today 85, 90 megabytes per second per drive, and that is state of the art. If the other vendor can't deliver that, find another vendor. Don't get confused with statements like hardware rate is superior. So yeah, there are some benefits on hardware rates in some very specific aspects, but at the end of the day, the only thing that matters is the implementation details. So if the implementation is right, you have things like context-aware I/O, which I can't overstate how critical that is. These other things all really don't matter that much, because it's really the key is how well integrated are all these different layers. Network matters. The majority of our problems we have also today in the field with spectrum scale is all around network. If it's not the storage, it's the network. And if it's not the network, it's the network. So it's always the network. RDMA can't be beat. So again, if people are very cautious about performance, you need to use an RDMA network. That doesn't mean Ethernet doesn't work. It's just significantly harder to get right. And it's typically far more error prone. And yeah, it cost me a lot of sleepless nights. So if you want to have something that's easier, RDMA. Critical here is get the right firmwares, the right drivers, and use the right releases. This is the biggest issue with RDMA networks. If the drivers and firmware levels are not right, it's going to get worse than TCP. But if that is taken care of correctly, you're going to be very happy with that. And so latency matters. So it doesn't really help to basically stack individual things on top of each other. So when we're talking about, and I don't want to bash other file systems, but when you look at most other distributed file system implementations, it's typically stacking of layers of software. And so I think only if you basically condense all these layers together to a very efficient layer, you're going to be able to tackle the first problem, the first part of the sentence, the latency. So if you want to really make use of Flash, you need a highly optimized file system for that. And we believe that spectrum scale is the right thing for that. OK, so this was the first topic. I know. The other going to be significantly faster, depending on how many questions being asked. The big problem is going to be the IOPs numbers. I guarantee you that. OK, but I'm trying to hurry over the next two because there's not that much. So a couple of data points I thought is very interesting to share. So what you see, or you probably can't even really see, is these top two lines that you see here is basically performance of an NVMe device with TSQS perf. So basically what I did is I run a block level performance number. So the top number, the top graph, maybe I actually should point at it. So this one over here, do you see that? Yeah. So the one over here is 4K random reads across the entire capacity of the block device. The next line is 4K random writes across the entire block device. So what I did after that is I basically created multiple files in a file system. In fact, I created 8 in total, and I will explain in a second why. But I basically created 8 files in a file system, and then I repeated the block test that I did run against the raw block device against the files. So I basically opened 8 files with 8 different processes and ramped up the number of threads. In fact, I only tested 4 different data points. It's 8, 16, 24, and 32. And so what you see is, you see essentially a difference between the block test here and the file system test here. So this gap between these 2 points is basically the latency overhead that the file system itself occurs at a single thread. Because it's basically 1 thread against block versus 1 block against 1 out of 8 files at the same time. And so you see there is a latency difference, but the difference is actually very small if you look to the right at what data rate we're actually performing. So the data rate here is almost 400,000 IOs per second. And again, this is all performed on a single node. So there's a single node with a local NVMe device, and it's actually at least the fastest NVMe device that I got my hands on. And I have a lot of NVMe devices in my lab. And so against the fastest device I could find, there is about a 30%, maybe 40% overhead of the file system compared to what the lowest overhead of the NVMe devices. So, but as soon as you ramp up the threads, you see basically over here, the file system almost has exactly the same performance like the block layer itself. So that means as soon as you increase the parallelism essentially works or helps overcome the individual threads latency problem. And you see essentially at about 24 threads, and that had also something to do why it took so long to catch up with the machine that I was using for the system, because it was a 3-year-old system that I was using for the test. With newer systems, that whole graph basically moved to the left. But you see that a single GBFS client can completely utilize at almost 600,000 IOs per second an NVMe device, which is a pretty high number for a single client. So yeah, that is also, so the question was, is that also an artifact of the driver? And the answer is partly yes. So I was not using the native NVMe libraries that you can use. This is actually using the block level emulation layer for NVMe. So there's also essentially additional latency involved because we're going through that layer versus talking directly with the NVMe device. So I expect if we would change GBFS to use the native NVMe libraries, also here we're going to catch up significantly earlier. And the end result would be higher, assuming the NVMe device would also be higher, because the NVMe device, as you see, also maxes out at around 550,000. So all of that could probably be increased. So the number you see down here, which is significantly lower, this is when you remote access device over an NSD interface. So this is now a remote client using the NSD protocol, running basically exactly the same test that I did run against the file system up here. So you see there is a significant higher overhead using the NSD protocol versus local. Again, we're talking about very, very high numbers here. The local latency on the device is about 10 microseconds. So given that the NSD protocol is adding a significant number of microseconds, you've seen somewhere in the range of when you look at the pure RPC layer, it's probably 20 to 30 microseconds. That's going to give us a significant hit here in terms of performance. Again, all these numbers also perform from a single client. So this is one client against one server having a local NVMe device in it. Okay, so I took this then to the next step and said, well, this is what we can get out of a local NVMe device. What can you get over a remote NVMe device who doesn't use the NSD protocol, but essentially uses the NVMe over Fabric protocol to actually get to the device? And so what I did here is I created a single LUN, and I created a file system later on top of that. So I basically performed exactly the same test, one time against the block device and the second time against a single file that resides in the file system on top of the block device. And so what you see is the blue numbers is the block level performance. The red number is repeating the same test again through the file system. And that's what I mentioned earlier. So the latency of GBFS is essentially so low that if you have to do the latency over the network, which essentially here is the same in both cases because the device is remote. It's using NVMe over Fabric, but it's a remote device. So the local super low level latency is not playing such a huge factor like in the previous chart. You see that with a single node, we can easily scale to around 240,000 IOs per second. And the block level performance is exactly the same like the file system performance. I mean, you can see there's like a 2 to 3% variation at the end, but it's not really that much more. So from that, I scaled this up. So let's try to run this against 8 nodes. And I did. And so what you see here is basically the curve, how that performs from one node, or actually from one thread to 128 threads against the same file system. So, but this is now not using the block level testing because I've proven already the block and the file level essentially performs the same. So that is only doing the file system level test. And as comparison, when you now take the single node result into that, you see that we scale from 1 node to 8 node by almost 97, 98%. So there's very, very little difference with that. And so on this 8 node cluster, I exactly achieved 1.6 million IOs from a single shared disk exported through NVMe to all the 8 nodes at the same time. So this were also not multiple LANs. This was one single LAN exported out of one single NVMe device. And all I did is basically scaling up from 1 to 8 clients and increase the number of threads that run against that single file system device. So again, I just wanted to share some NVMe numbers because I know everybody's talking about it. So to give you some reference points, how well Spectrum Scale actually performs under these type of conditions. I heard another question this morning about, we don't want to hear always about the 16 meg block sizes. So I ran a couple of tests a couple of weeks ago. I have another test with 512K, but I did not include that in the charts before. I should have probably changed that this morning. So these are IOR numbers to see the performance of the GF systems. And somebody asked earlier about, okay, how many lower block size IOs can I expect or bandwidth can I expect out of it? So the good news is with the deep flash system, I haven't done yet 32K, 64K, or even smaller block size tests, but we've done block size as low as 512K, and that is 512K rated. So this is through the GNR layer. So the block size is 512K, but given that we use an 8 plus 2P, there's obviously significantly smaller, basically 64K increments underneath. And so with a 1 megabyte block size, you get about 9 gigabytes per second on writes and 13.5 gigabytes per second on read. This is with a single enclosure. So this is basically rated with the GNR code. And the 512 numbers are essentially exactly the same. So it doesn't matter if you run 512 against it or 1 megabyte block size against it, you essentially get exactly the same performance numbers. So if you go to the GF2, you see there is an almost linear scale. There's a little bit of a loss in the top 5 percentile or so, but it's essentially roughly 17 gigabytes per second on write and almost 27 gigabytes per second on read. Also, this is done with a 1 megabyte block size. Again, if you would use 512, you would get essentially exactly the same results.
What's the difference between the GF and the GF2?
Oh, sorry, I'm not sure. I thought that was explained this morning. The GF1 is the ESS system with 1 deep flash device. The GF2 is the ESS system with 2 deep flash devices. So these are 2 half-popped DF150 devices. So that is basically the system that has 2 shelves attached, each with 32 modules, so total of 64 modules in the system. Okay, so let's start with the first headliner. What are IOPs and why is there so no answer to how many IOPs does an ESS GX system question? It's very simple. When people ask about IOPs, they already ask the wrong question. IOPS is not a file system metrics. You cannot answer a question about IOPS if you don't specify what an IOPS actually is. In the block world, this is typically pretty simple. When people talking about IOPS, they talk about some 4K random read-write workload. In a file system, that doesn't really exist. Why? Because typically when people do reads and writes, they also do creates and deletes and renames and links and unlinks and a gazillion other operations. So there is no direct translation between a block layer, IOPS, 4K random read or write or whatever performance number to what can a file system deliver. It's just impossible. Plus, there is so many layers of complexity in between, and I have actually some really cool examples for you to look at that proves my point pretty well. So when you're talking about IOPs in a concept on a file system, you need to first specify what layer you're talking about. Because in block, it's very simple. There's this controller thingy, it has fiber channel cables coming out. I hook this up to a node, I open a LUN, and I do 4K random reads, writes to it. Very simple. This is something I can explain to somebody. This is something that's easy to measurable, and everybody's going to be able to repeat that. If somebody tells me I want to know how can I do 4K random reads, that's to just pick one in a file system, where do I start measuring? And most importantly, how do I actually measure that? Because the how is going to make a significant difference. So without specifying absolutely down to every single level of detail, it's impossible to answer that question. So because there is different layers, so it starts at the block level, as I said, this is simple. This is you open a LUN, do read, write, sequential, random, whatever pattern you want. When you go to the NSD server, a traditional NSD server, although that is typically pretty simple, because whatever request you send to the NSD server translates one-to-one into a disk I/O operation. As soon as you're taking GNR into the picture, it gets super complicated, and therefore I'm not even going there. I'm only trying to explain that on the example of a traditional NSD server. Because as soon as GNR gets involved, it has the context of the I/O, there is very complicated caching layers happening already on the NSD server level. So it may be that the majority of the I/Os don't even make it to the disk or not even coming from the disk. Because compared to a traditional NSD server, the GNR software is a cache controller, is a RAID controller in software. Has its own caching layer and everything. So it's really hard to actually even measure that. Then you go to...
Would that be true even for read IOPs?
Yeah, sure. So you can buy an ESS system today with 256 gigabyte of memory. And we're actually approving an RPQ pretty soon. You're going to be able to put 2 terabytes of memory into an ESS system. So you have a 2 terabyte read cache in the ESS system that is completely managed by the context I/O-aware cache layer inside the GNR layer. So when you do a read, let's say you do a benchmark, or let's say your working set is going to be 2 terabytes in size. If your working set is going to be 2 terabytes in size, it's going to fit entirely into the cache. None of the I/Os you're going to do, read I/Os against the system, ever hits a single disk drive. They always will come out of memory. And so it's... The GNR layer caches. It has nothing to do with the client. That's why I'm saying, if you take a traditional NSD server, it's just an I/O proxy. You send a write request to it, and it simply executes a write request. If you submit a read request, it submits a read request to the storage subsystem. GNR works very differently. If you submit a read request to GNR, it might decide to read a little bit more from the disk because of surrounding checksums or whatever. If the next request comes in, you might already get a cache hit, even the first request never asked for it. So it's really complicated. You can't easily put this into a formula that somebody can calculate that. So as soon as you're now on the spectrum scale clients, which could also be protocol nodes, it's going to get even harder. So spectrum scale clients have prefetching, they have write behind, they have all kind of very intelligent heuristics, when to read surrounding data, read behind data, read more data advanced. I mean, there's so many techniques in it. A simple request of 100% random reads or writes with direct I/O, that is something that's easily measurable. But why would you actually measure it? There is no application on the planet who would ever do that. So yeah, you could create and craft a benchmark that forces every single I/O on this top layer to turn into exactly one single I/O on that bottom layer, but this is not what any application would ever do. So when it gets even more complicated when you now involve even the client or the application, because depending on what your client and application does, if you're using NFS, for example, as a protocol, it on top adds its own layer of caching and stuff like that. So it gets very, very complicated. So but let's do a very simple IOPS test on a file system to actually prove my point. So what you see here is, this is an IO zone run that was running across 90 nodes. It was only 90 nodes because one got defect when I wanted to run the test, so I couldn't use 20. So it's going to be 19 nodes, unfortunately. So I run this test, and what it basically does is it runs IO zone in clustered mode. Clustered mode is it spawns IO zone across a larger number of nodes and performs the requests that I ask it to do. And the request is, for every single thread it starts, it's going to read or operate on a total of 32 gigabytes of data, and it's going to do 4K requests out of that system. And given that this is done with O, it's going to do this essentially sequentially on the system. So what you see here is now the results of that combined I/O zone test. So you see that on the top line, you see the number of operations. So the 76 initial writers performing the test together, let me read that correctly, it is 5.8 million IOs per second. Oh, sorry. Yeah, thank you. Top one? Yeah. So it's 5.8 million IOs per second. So great. My GL6, which only exists out of spinning drives, can do 5.8 million IOs and probably beats actually pure flash-based storage systems by, I would say, almost an order of magnitude. So the rewrites are still 5.9 gigabytes per second. So on the reader side, it gets even faster. It's 7.1 million IOs, and the reread is also 7.1. So given that the size was big enough, because again, I used a total of, I think, 76 or so workers, that means the overall working set was 2.4 terabytes in total. That exceeds all the caches in all the systems together by multiple factors. So when I calculated, there may be something around a 5% cache hit rate as part of that. So that means the write test performed 5.9 million 4K IOPs, runs at around 23.7 gigabytes per second, and the retest performed 7.2 million 4K IOs per second. So I shared these great numbers with you to then, after that, disappoint you to tell you that this number, using my French, is bullshit. So why is it bullshit? Very simple. Because what I did is, I ran a perfectly legitimate test of doing 4K reads out of a file system to get an IOPS number. But because I was using 4K buffered reads for that test, basically all of the 19 nodes under the cover, while the application only did read 4K, so it's not bullshit that the application read actually, 7.2 million IOs per second, the storage subsystem itself had to do significantly less work. Why? Because every time I did a 4K read, we basically looked ahead and said, oh, he's doing multiple 4K reads. Let's prefetch data in larger IOs. So the client actually submits prefetch requests to the storage system. On the storage system, you're going to see full track. I think this was using 8 megabyte block size, if I'm correct. And this test was even done with a GPFS 3.5 release, because the numbers I have here I pulled out of a chart deck I created 4 years ago. So just 1 second. So basically what I'm trying to say is IOPS numbers are meaningless unless you define exactly what you're looking for. So if I would have repeated this test with, let's say, direct I/O, the numbers would have looked already very, very different. Because now with direct I/O, the client is not allowed to do prefetching of IOs, which means every request would have gone to the storage subsystem. There is still prefetching now done on the storage subsystem level, depending on which device you're using. So it's still not a 100% equivalent test to the block level test. All I was trying to point out is, if you just ask for IOPS, I can give you every number you want, and I can essentially guarantee you it doesn't reflect what you or why you asked the question in the first place. So therefore, either don't ask for IOPS or be very, very specific what you're actually trying to achieve. And another point, converting IOPS in metadata operations is the next big mistake. Probably for the next session that we're going to do, I should probably take a single topic for 1 hour and just talking about testing performance and metadata operations on a file system, because that's an art by itself. And in the most cases, people are going to be surprised. It has very, very little to do with storage. Metadata operations, while at some point in time end up on storage or might be read from storage, the majority of the metadata performance is actually depending on client-side tuning. It has very little to do with storage performance. Okay, and now Dean gets his 5, maybe a few more minutes talking about Docker.
So hi, my name is Dean Hildebrand. I work with Sven at the IBM Research Center. So I just wanted to talk briefly about some of the work that we've been doing around investigations of using containers with Spectrum Scale. For each of you, depending on your role, you might have a different view of what Docker and containers is used for. You know, if you're a system administrator, you might see users coming saying, hey, I want to use this. If you're developing a file system, you might say, isn't this for Amazon? Why are we worried about this? Again, all independent on where you are and how your apps are running, you know, you have a different view. But they have a lot of value. They're no longer just for running, you know, and load balancing jobs on top of Amazon. And so we're already seeing requests coming in for, okay, you know, we have containers, we want to run them. What's the best way to do this with Spectrum Scale? So I didn't want to, again, I only have a few minutes, so I didn't, you know, I could spend, I don't know about 2 hours like Sven could on the IO side, but I could definitely spend more than 5 minutes. But again, at a high level, the use cases where containers are being used is expanding. You know, just the show of hands, I guess, in this audience would be how many people have been, you know, either looking into it or, you know, investigating or have been asked by their users to say, you know, do you think I could run this in the future? Yeah, so it's about, what, about maybe 20, 30% already in terms of the types of questions. So this is where we come in. We're trying to help you, you know, along the way. We want to work with you. You know, it's different when we were looking at cloud technologies like OpenStack. It was simply a system administrator, I think, driven exercise, whereas now you have users, again, showing up and saying, I have this thing and I want to run it. So, you know, how am I going to do it? So again, the areas where it's people are running them is getting a lot more larger. People are running just even their standard apps that they, you know, the traditional apps, they're Dockerizing them and being able to deploy them just to alleviate portability and deployment and many other resource utilization. But HPC and scientific computing is also getting a lot of traction in this area as well for that exact reason, right? Developers, scientists want to be able to run their apps on different supercomputers. They want to use different clusters. They want to have the portability, and this is a way to do it. So with Spectrum Scale, there's a couple different advantages that you'll see when you're using Docker. Some of it is right off the bat. You can take any point in your file system and expose it to a limited set of containers that are run. So right there, you're achieving a level of multi-tenancy that this set of containers can see this set of data and this one can see that. That's something that, again, we've always struggled with GPFS and Spectrum Scale in terms of providing that level of multi-tenancy. And I don't think the community is there yet, but if you can get it right, this is something you can achieve right off the bat. Another clear benefit right off the bat is that as opposed to virtualizing your data center and then providing, you know, GPFS inside of the VMs and these types of things, you're not getting any performance degradation by running containers on top of your file system. It's as if you were just simply running it on your standard POSIX-based file system. So there's not any performance loss by containerizing your apps to GPFS. That is if there were, if you, let's say, put it in a VM and then you have to do complicated networking to get all of that stuff, or you have to switch to using NFS, so there's other complicated matters. Another one is that relatively new in Docker is something called user namespaces. This gives you the ability to give users any user IDs inside the container, including root, and you can map them to some other set of user IDs at the host level, and that's where Spectrum Scale would play. And so they can have sort of a limited root ability in their container, and you can map it to some other user ID in the file system and not having to worry. So it's somewhat alleviating, I'm not saying fixing or solving, but alleviating the root concerns, security concerns that we've had as well. So just again, to try to wrap up really quickly, there's sort of a longer road here, I think, around containerization and OpenStack and how they work together, and whether you should be deploying bare metal and should you be deploying in VMs, and you know, there's a longer conversation. One of the initial steps that we're taking is more of just the bare minimum initially is writing what's called volume drivers. Kubernetes has their own set of volume drivers when it orchestrates Docker. Docker has its own set of how it manages volume drivers. Volumes are essentially just the data sets that the applications are using inside the container. And so we're writing plugins. We're, you know, in the research side, and a framework in order how you could use them. You can then use Kubernetes and Docker commands in order to provision storage and link it into the containers that you're running. So this is something that we want to release, and we would like to work with you in terms of getting it right and ensuring it has the features that you'd like to see for your applications. So if you are interested in this area, please come talk to me afterwards, and I can give you a longer discussion about how that would work and how we're going to. We haven't quite figured out how we're going to release this yet, but the key point is to release it as sort of more of a research item and get valuable feedback before it's integrated directly into the product.